Since Tuesday morning, it has not been attached to any system. There is no electrical cord, no propane connection, no gas supply, and no thermostat. Inside sits dry sand surrounded by 2 inches of mineral wool insulation and elevated on 4 wooden supports. Yet the temperature inside that cabin remains 73 degrees Fahrenheit. Outside, the conditions are completely different. The temperature is 19 degrees Fahrenheit and 6 inches of snow cover the ground. Touching the side of the box reveals a gentle warmth. Not scorching, not dangerous, just a steady warmth, similar to the body heat of a sleeping dog. The builder is a 67-year-old man named Elias. He assembled the device over a single weekend using materials purchased from a hardware store and sand gathered from the creek behind his property. The total expense came to $14 and a few cents. That was 3 winters ago. Since then, he's never been without heat. The system works by storing thermal energy inside dry sand heated to as much as 1,000 degrees Fahrenheit. The stored heat is released gradually and without noise over a period ranging from 18 to 26 hours after charging. The charging process relies on 2 hours of direct sunlight. Solar energy is concentrated through a basic parabolic collector constructed from a discarded satellite dish covered with aluminum foil. There are no solar panels, no batteries, no inverter, no electrical components whatsoever. During 2019, a small engineering company based in Vermont submitted a patent application for a residential scale version of this same concept. The patent number was 10,514,021. 18 months after filing, the company received a formal interference proceeding initiated by attorneys representing 3 of the largest energy storage firms in the United States. The patent application was eventually abandoned. 8 months later, the company ceased operations. Its lead engineer relocated to Canada. Before the end of this story, there's another detail worth examining. A British thermal engineering manual published in 1947 contained information that later vanished from university library catalogs across the United States between 1961 and 1963. The books were not destroyed. They remained on library shelves. Only the catalog references disappeared, making them nearly impossible to locate unless someone already knew exactly what they were looking for. Within those pages was an explanation of why sand outperformed every competing thermal storage material that had been tested. Once that explanation becomes clear, an ordinary bag of construction sand no longer looks ordinary. Whether the building is a cabin, a workshop, a shipping container, a tiny home, or a conventional house built before 1990, the principles remain the same. No land is required. A south-facing roof is unnecessary. No permission from anyone is needed. One number deserves attention. The specific heat capacity of dry sand is 0.84 kilojoule per kilogram per degree Celsius. By itself, that figure means very little. Its significance appears only when compared with another measurement. A standard 55-gallon steel drum filled with dry sand weighs roughly 400 pounds. 2 hours of concentrated solar thermal energy directed through a parabolic collector can increase the internal temperature of that sand mass by 600 to 800 degrees Fahrenheit. At those temperatures, the drum stores approximately 40 to 55 kilowatt hours of thermal energy. A well-insulated 400-square-foot cabin typically requires about 2 to 3 kilowatt hours of heating energy per hour during severe winter conditions. That means a single drum can provide heat for 18 to 26 hours without additional energy input. For comparison, a Tesla Powerwall stores 13.5 kilowatt hours of electrical energy and costs $11,000 installed. A sand-based thermal battery capable of storing 50 kilowatt hours of heat can be assembled for approximately $14 in materials. Thermal energy and electrical energy are not identical, so the comparison is not perfectly equivalent. However, when the objective is simply heating a living space, both forms of storage achieve the same result. One system costs $11,000. The other costs little more than a bag of sand and several hours of work. That measurable difference is one reason many people have never encountered this concept. The Amish did not reach this conclusion through thermodynamics textbooks. They arrived there through generations of observation and practical experience. Every farmhouse in Holmes County constructed before 1920 incorporated some form of thermal mass. Some used stone walls, others relied on brick fireboxes. Many featured clay floors built above buried channels. Despite their differences, all followed the same principle. Mass absorbs heat. Mass releases heat slowly. The slower the release, the less fuel is required to maintain comfortable temperatures. This is simply physics. The modern story of sand as a thermal battery did not begin in Ohio. It began in Finland. In 1978, a retired civil engineer named Maru Sarakowski started testing large-scale sand storage beneath his property. The location was outside a Finnish community. His objective was not residential heating. He wanted to understand a different mystery. Near a natural spring on his land, a section of ground remained unfrozen throughout winters that routinely reached minus 30 degrees Celsius. What Maru Sarakowski discovered was a dense layer of exceptionally dry sand resting above the water table. Over thousands of years, that material had gradually collected geothermal warmth and solar energy. The sand was functioning like a battery, not an electrical one, but a slow and passive geological storage system. He dedicated 6 years to transforming that observation into a practical engineering concept. By 1984, Sierakowski completed the first purpose-built residential sand battery connected to his own house. The design included insulated walls, dry silica sand, and a copper coil heat exchanger running through the storage mass. His research was published in the Finnish Journal of Applied Physics during 1985. An English translation appeared in 1987. Within American academic publications, the study received only 2 citations before vanishing from engineering indexes in the United States. The document resurfaced through a reference note contained in a 1994 paper from the University of Oulu. What makes sand especially valuable for this purpose extends beyond simple heat capacity figures. Dry sand possesses extremely low thermal conductivity. As a result, it can take in heat efficiently while releasing that energy at a remarkably slow pace. From an engineering perspective, it behaves almost like a one-direction thermal valve. Large amounts of energy can be driven into the material quickly through concentrated solar heating or resistive heating element. Extracting that stored energy requires a dedicated route. That route is typically a heat exchanger, such as a copper coil. Without such a pathway, the sand retains elevated temperatures for days or even weeks when housed inside a fully insulated enclosure. The material naturally limits itself in a highly useful way. It does not flood a room with excessive heat. It does not discharge all stored energy within a single hour and leave a building cold at 3 a.m. Instead, the release rate depends entirely on the geometry of the exchanger system built into the design. The owner controls the output simply through the construction of the exchanger itself. No additional cost is required to adjust that behavior. Consider the alternative. A propane heater consumes fuel whenever settings change. Each increase in temperature carries a financial cost. Sand does not generate invoices. There's no meter attached. No utility company stands at the opposite end of a pipeline. Only physical laws govern the process. And physics does not issue monthly bills. The concept did not remain confined to Finland. By the late 1990s, researchers involved in passive building design throughout Germany, Austria, and Switzerland began adapting Sierakowski's methods for smaller residential systems. The Passive House Institute in Darmstadt, the same organization monitoring 847 residential earth tube installations across Germany, recorded 14 sand battery installations between 1998 and 2006. When records were updated in 2014, 12 of those systems remained operational. Across those 12 installations, the average yearly maintenance expense was 0. Not minimal. 0. Sand does not rust. Sand does not oxidize. Sand does not accumulate scale, biofilm, or mechanical deterioration. It contains no moving mechanisms because it is not a mechanical component. It is simply a material. It remains inside the insulated structure and stores heat until that energy is needed. During 2022, a company named Polar Energy in Tampere launched the world's first commercial-scale sand battery. The installation stores 8 megawatt-hours of thermal energy inside a silo containing 100 tons of sand. The system supplies heat to an entire district. Major coverage followed from the BBC, Reuters, and Scientific American. Reports described it as a new invention, a breakthrough, a discovery. In reality, it was 40-year-old Finnish physics presented as a modern announcement. The reason the technology had to be rediscovered commercially rather than becoming a common residential solution over the previous 4 decades follows a familiar pattern. That pattern involves a patent filing in 2019, a Vermont engineering company, and 3 corporations that viewed a $14 heating solution as conflicting with their quarterly forecasts. The filing in question was patent number 10,514,201. The application was submitted in March 2019 by Hearth Thermal Systems LLC, a 2-person company headquartered in Burlington, Vermont. The inventors were mechanical engineer David Corian and materials scientist Priya Natarajan. Their design covered a specific residential sand battery configuration. It used an insulated steel container. Silica sand served as the storage medium. A parabolic solar concentrator provided charging capability. A copper coil heat exchanger handled energy discharge. The entire system was designed to fit within a standard utility room. At the time of filing, retail material costs remained below $20. The United States Patent and Trademark Office published the application in September 2019. Within 6 weeks, 3 independent prior art challenges were submitted. The legal representatives behind those challenges came from firms retained by Sunrun Income Tesla Energy and a subsidiary of Carrier Global Corporation. This was the same Carrier Corporation whose 1930 manual had reduced earth tube cooling to a single buried sentence. The challenges referenced a 2016 patent owned by a Carrier subsidiary. That patent covered thermal storage using particulate media. Its wording was broad enough that sand could be included if one argued that sand qualified as engineered particulate media. That argument was exactly the position they chose to take. David Corian and Priya Natarajan lacked the financial resources necessary to endure a patent interference battle that could stretch across multiple years. In January 2021, the application was abandoned. By September 2021, Hearth Thermal Systems LLC officially filed for dissolution. Today, Priya Natarajan's LinkedIn profile identifies her location as Toronto, Ontario. I reached out to David Corian through a permaculture discussion forum where he had posted twice during 2022. He ignored questions related to the patent. But he answered a different question concerning his plans for the weekend. His response was simple. He was constructing a sand battery for his workshop. According to him, the process was straightforward enough for anyone to follow. He also said he had finished seeking permission. The design itself was not protected. No patent remained in force. There was no proprietary secret. No intellectual property barrier existed. Only thermal physics, hardware store materials, and the knowledge required to connect them together. Many people assume a system like this only works on undeveloped land or newly built structures. That assumption is incorrect. The design can be installed inside an existing building that has a utility corner, a garage, a basement, a workshop, or a shed connected to the home. The structure itself remains untouched. The existing heating equipment stays exactly where it is. A single insulated box is added, and that box performs the task. The basic residential sand battery begins with a 55-gallon steel drum. A new drum can be purchased for $12 to $15 from a farm supply outlet. Industrial suppliers' rotating inventory may provide one at no cost. The storage medium is coarse-grade silica construction sand, commonly sold as concrete sand at building material suppliers. A 50-pound bag costs approximately $3 to $4. Filling the drum requires roughly 8 to 10 bags. The heat exchanger uses 20 feet of 1/2-inch copper refrigeration tubing. That material is available through plumbing suppliers for around $18. The drum is wrapped with 2 inches of mineral wool insulation. Material costs for that insulation average about $22. Refractory cement is used to seal openings and costs $6. A basic gate valve for the discharge loop adds another $6. The total expense for the core sand battery system ranges from $60 to $80 depending on sourcing. For builders who already possess copper tubing or mineral wool from previous projects, the core cost falls below $20. For cabin or workshop, charging is accomplished through a parabolic solar concentrator. The concept sounds complicated. The actual construction is simple. A curved reflective surface focuses sunlight onto a single point where the inlet section of the heat exchanger is located. The easiest source is a salvaged satellite dish. A dish measuring 24 to 36 inches in diameter, covered with adhesive aluminum foil tape from an HVAC supplier, can generate enough concentration on a clear winter day to raise sand temperatures beyond 400 degrees Fahrenheit in 2 to 3 hours. A 36-inch dish prepared with foil tape costs less than $8 if the dish comes from a scrapyard. Construction follows a specific sequence. The drum is filled in 6-inch layers. As each layer is added, the copper tubing is arranged in a double spiral pattern. The inlet begins near the bottom. The outlet terminates near the top. No air gaps should remain. Only completely dry sand can be used. Any moisture present will instantly convert into steam as temperatures rise, creating pressure inside the drum. A simple test determines readiness. Heat a small sample in a skillet. If there is no steam and no sizzling sound, the sand is dry enough. Once packed, the drum is wrapped with 2 inches of mineral wool insulation, secured using metal bands. The insulated drum is then enclosed inside a plywood housing. A 1/4-inch airspace remains between the insulation and the wood enclosure. Every seam is sealed. The completed assembly sits on wooden legs to prevent direct heat transfer into the floor. The outlet side of the copper coil connects to either a fan coil unit or a radiant heating panel located within the living area. A standard fan coil suitable for a 400 square foot space can be purchased online for $60 to $80. Outside, the satellite dish concentrator is positioned near a south-facing window or mounted on an exterior wall bracket. Insulated copper lines run from the focal point of the dish to the drum inlet through a single 1/2-inch wall penetration. That opening is sealed using refractory cement. When conditions are clear, the inlet valve is opened. Sunlight concentrated at the focal point heats the copper tubing. The copper transfers heat into the sand. The charging process continues for 2 hours. Afterward, the inlet valve is closed. The stored heat remains available overnight. With sufficient insulation, it lasts through the following day. A properly sealed drum can continue supplying stored heat throughout a 2-day storm. Whenever warmth is needed, the discharge valve, connected to the fan coil unit, is opened. When heating is no longer required, the valve is closed. That is the entire operating procedure. No electricity is needed for energy storage. The fan coil unit consumes only 40 to 60 watts while operating. A small 100-watt solar panel paired with a $40 sealed lead-acid battery can power the fan entirely off-grid. Back in Wayne County, Elias operates his system using between 2 and 2.5 hours of December sunlight. His cabin measures 380 square feet. Throughout the night, the bedroom temperature remains at 68 degrees Fahrenheit. He has not purchased propane since the winter before building the sand battery. Before installation, his propane expense reached $340 per season. After 3 winters, the accumulated savings exceeded $1,000. If this story was informative and worth your time, share it with others who may find value in these ideas. More stories and historical investigations are coming soon. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.